In this video, we present BIT, a smart textile interface that operates without the need for embedding batteries, integrated circuits, and connectors into textiles. It features with a receiver coil, enabling wireless sensor data acquisition with a reader through magnetic coupling. BIT can be designed to support various types of sensors and concurrent operations of up to 3 sensors, making many textile objects to become interactive while preserving the passive nature. Advancement of smart textile technologies grants daily wearables like garments and gloves the ability to sense various user inputs. However, many of current textile sensing techniques require the embedment of batteries, integrated circuits, and connectors into textiles. This leads to challenges in manufacturing, usability, and e-waste issues. To address these challenges, we introduce BIT, a battery-free, IC-less, and wireless smart textile interface. BIT consists of multiple resonant circuits connecting to a receiver coil. Each resonant circuit includes a sensor that functions based on capacitance, inductance, or resistance. During operation, a reader featuring a transmitter coil wirelessly couples to the receiver coil on the smart textile interface through magnetic coupling. This induces a current within the smart textile interface to power the sensors. When a user interacts with the sensors, it alters the sensor values and causes a shift in the impedance spectrum of the smart textile interface. This shift is ultimately reflected in the reader circuit's impedance spectrum. Thus, by measuring these changes, our system applies a mathematical model and algorithm to extract sensor values, enabling the detection of user input. To guide the design of BIT, we conducted a series of experiments to identify and optimize factors that affect the system's performance and robustness. This included refining the designs of transmission lines, receiver coils, and transmitter coils. Then, we developed an algorithm that can extract multiple sensor values from the measured impedance spectrum based on the equivalent circuit model of the entire system. To validate the accuracy and robustness of this approach, a simulation-based experiment was conducted, which demonstrated high performance in extracting sensor values from the impedance spectrum. To demonstrate the potential of BIT, we designed and implemented 2 interactive prototypes, an interactive shirt and a glove. This shirt has a receiver coil on the front pocket, a capacitive pressure sensor on the shoulder, a resistive button array on the sleeve, and an inductive object detector on the lower pocket. When the reader, resembling a smartphone, is placed in the front pocket, its transmitter coil aligns with the receiver coil on the smart textile interface. This enables our system to wirelessly measure impedance spectrum and concurrently monitor sensor values. In turn, the system can identify which button is pressed, detect the type of metallic object placed in the pocket, and measure the pressure on the shoulder. This was all achieved without embedding batteries or ICs into the shirt. In addition to the shirt, the glove is another textile product closing to a device which may feature a coil, like a smartwatch. We fabricated an interactive glove that included bend sensor on thumb, index finger, and middle finger respectively. When reader is placed, our system can monitor the bending circumstances of 3 fingers. With this glove, different hand gestures can be robustly recognized. For more details about this work, please see our paper.